In this work, we present a 3D human reconstruction framework, Pifu HD, that recovers facial details of the person in 3D at 1K resolution from a single image fully automatically. Many human reconstruction methods rely on a parametric model for regression. However, the prediction is typically a naked body, and all the personal details such as hairstyles and clothing are ignored. On the other hand, model-free regression approaches have demonstrated higher flexibility and expressiveness. As a result, we can recover details present in the input image more accurately. However, the previous methods rely on explicit shape representations such as voxels, limiting the resolution due to high memory footprint. To address the resolution limitation, last year we proposed pixel-aligned implicit function, Pifu. I will briefly explain how it works and point out its limitation for the more precise human reconstruction, which is the main focus of this work. In Pifu, we use neural implicit function for shape representation. 3D shapes are represented by the label set of occupancy fields parameterized by a neural network. Since this formulation does not involve any discretization, we can effectively model 3D shapes at an arbitrary resolution. Early works including occupancy network encode an input image as a global descriptor to reconstruct corresponding 3D shapes. However, this way, the network does not leverage spatial relationship between queried 3D points and the input image. To address this issue, we introduced pixel-aligned implicit function, where we utilize free convolutional image features to associate queried 3D point and the projected pixel coordinate. Given the pixel-aligned code and the queried depth value z, we can infer 3D occupancy fields in a pixel-aligned manner. However, we found that the reconstruction quality is still bounded by the feature resolution of an image encoder. The original Pifu implementation utilized an image encoder that has done sampling operation to keep the spatial resolution small for the following reasons. First, small feature resolution allows heuristic reasoning, as 3D reconstruction requires absolute location of where the surface is. Holistic reasoning is indispensable. Moreover, small resolution allows us to train the model with a reasonable amount of time. The downside is limiting the expressiveness up to the small resolution, resulting in less detailed reconstruction than the original input image. What about utilizing a shallow but high-resolution image encoder? Although the result becomes sharper and more detailed, the reconstruction is prone to artifacts due to the lack of global information. In this work, we address the disadvantages of both architectures by a coarse-to-fine multi-level approach. There are several human reconstruction methods that utilize a coarse-to-fine strategy. However, I argue that these existing methods have several limitations. The existing approaches also leverage the memory efficiency from the coarse model and detail from the inferred surface normal. But the base geometry tends to be low fidelity, and any detail hallucination on top of inaccurate base geometry does not provide faithful high-resolution geometry. Thus, we introduce a latent multi-level representation. First, we train the coarse Pifu as in the original Pifu implementation. And we viewed the intermediate latent feature of the MLP as a 3D embedding. And the fine image encoder takes a 3D embedding learned from the coarse Pifu instead of the queried depth value. This way, the fine module can easily perform at least as good as the coarse module, as the omega provides all 3D information used to make the coarse prediction. Additionally, the fine image encoder can fully focus on geometric details that the coarse module is unable to provide. Unlike the existing coarse-to-fine approaches, we directly predict high-resolution 3D geometry without any post-processes. In summary, our latent multi-level representation achieves high-fidelity detailed 3D reconstruction in a memory-efficient manner. I will show you our reconstruction results from video sequences. Now we can recover highly detailed geometry from a self-captured video, frame by frame, not only for the front side, but also for the back side. Note that they are raw outputs from Pifu HD without any post-processes. We have also improved the fidelity of the backside geometry by conditioning the network with the inferred surface normal for the backside. Please check out our paper for details and the ablation studies. Thank you for listening.